In this scenario, we are trying to measure the caffeine content of our favorite coffee brand. So our approach is that we're going to have to not be able to directly measure the caffeine content of our coffee, but rather indirectly measure it. And we can do that if we can find some property of our coffee or some other caffeine-containing substance that is related to the caffeine content of our beverage. And so it turns out that with caffeine, one of those properties that is related to the caffeine content, something that we can measure, is something called the absorbance. So the absorbance at 274 nanometers, wavelength at 274 nanometers, does turn out to be proportional to the caffeine content of a solution. So our first task is that we first have to first determine what the relationship is. So in order to do that, we have to first create several solutions of known caffeine content. We create those solutions, and then for those various solutions, we measure the absorbance at 274 nanometers to find what that mathematical relationship actually is between what I can measure and what I'm actually interested in. So when we did that, we found that there is a relationship. It's a positive relationship. As one goes up, the other one goes up, and turns out to be a fairly linear relationship. So with Excel or some other spreadsheet program, we can use the program to come up with the equation for this linear trend line. Y equals 0.0105x plus 0.0049. This is the form of equation for a line. Y equals mx plus b, where m, in this case 0.0105, is our slope, and b is the y-intercept, 0.0049. What's nice about this equation is that once I have this mathematical relationship, if I then have an unknown solution whose absorbance I'm able to measure, I can then use this equation, plug the value y in, and then calculate for x, estimate then, in this case, the caffeine content of my coffee solution. So to do that, I want to first take my equation 2.1, and first rearrange it to solve for x. So to do that, we will first take our, whatever value y happens to be, subtract from that the 0.0049, the y-intercept. In the algebra, I'm trying to isolate my variable of interest. So I'm first going to subtract off the y-intercept, and then I'm going to divide by the slope. When I do that, I can now isolate the value of x, which then allows me to very simply plug in any value y, and then from that solve for x. So when I plug in my value y that I determined for my unknown coffee solution, x is equal to 0.378. The value y I found for my coffee minus 0.0049 divided by 0.0105. Put those numbers into our calculator. We get 0.378 minus 0.0049 divided by 0.0105. And we get a value of x of 35.5. And we'll keep an extra digit or two by 3. And that's our value, that's our number. But of course, these numbers also have to have units attached to them. And because this is x, then the units for my value are going to be always the same as the units of my x-axis, which in this case are milligrams of caffeine per 100 milliliter solution. So that is, in some sense, my answer. That is the caffeine content of my coffee solution, 35.53 milligrams caffeine per 100 milliliter solution. But if I wanted to determine how accurate my value was, like we talked about last week, in order to determine accuracy, calculate percent error, I need a true number. And so I go on the web or I look up the label, and I find that for this particular coffee maker, they claim that the true caffeine content of my coffee is 43 milligrams of caffeine per serving. So if I want to compare my value that I found to the true value I have to make sure I'm comparing apples and apples. It has to be a fair comparison. And it's not quite, at this point, it's not quite a fair comparison because the true value has units of milligrams caffeine per serving, and my experimental value has units of milligrams caffeine per 100 milliliters of solution. And that may or may not, that may or may not be in fact a fair comparison. We don't know yet quite what a serving is. Well, if I look at the label again, I found the serving is not 100 milliliters, but rather it's 120 milliliters. So to compare this value to this value, I need to convert this value from units of milligrams caffeine per 100 milliliters to milligrams caffeine per serving, so I can fairly compare the two. And so to do that, we have to do a simple dimensional analysis process where I have these units. So my units, I plan here. I have units of milligrams of caffeine per 100 milliliters. That's my value I found from my equation 2.1. And I want to convert that to what's on the label, which is in milligrams of caffeine per serving. So if you do analysis, notice that the only thing we need to change, only thing we need to work on, numerator is fine, milligrams caffeine is perfect, but the denominator needs to convert from 100 milliliter solution to servings. So I can do that because I know what a serving is, so I'll use this as my conversion factor, and we find then we have 35.53 milligrams of caffeine per 100 milliliters of solution. Using our definition of serving as our conversion factor, as always, we want to make sure our units work out like they're supposed to. So I want to get rid of milliliters of solution. I'm left with servings. So I want to put milliliter solution on top. I'm going to put servings on the bottom. And according to the label, one serving is equal to 120 milliliters. So when I do my calculation, notice that milliliter solution units cancel. I'm left with milligrams caffeine per serving, which is exactly what I want in my final answer. So we have 35.53 times 120 divided by 100 gives me a caffeine content of 42.64. And to probably the three significant figures we have, and assume that this number only has maybe three significant figures. We assume it's significant. Then this would be 42.6 milligrams of caffeine per serving. So now I can finally fairly compare my experimental value, 42.6 milligrams of caffeine per serving. It's exactly the same meaning as 35.5 milligrams of caffeine per 100 milliliter solution. Different numbers because they're different units, otherwise same meaning. Now I can fairly compare because these units of my experimental value now match the units of the true value. So finally, we can then calculate percent error like we did last week. Percent error, if you recall, is going to be our experimental value minus the true number divided by the true number times 100%. Percent error then in this case is going to be equal to experimental value, which is the 42.6 milligrams. The unit, just make sure the unit is like it should be, minus the true number, which is for the label 43 milligrams caffeine. All divided by the true number, which is 43 milligrams of caffeine per serving. And then we plug all our values in, we get a percent error of 42.6 minus 43 divided by 43 times 100%. And we get a value of about negative 0.93%. So percent error, negative 0.93%, less than 1% difference between relative difference between my experimental value and the true value. And it's a negative number, which means that my experimental value is less than the true value.